Hi, everyone. So in 5.3, we're going to solve another equation that's nonlinear in a trig function. In this case, it's third degree, or cubic, in sine of x. This is way more complicated than the last problem we did, so something as simple as the square root method won't work. Here, it turns out we're going to need to do some real factoring. Now, you may look at this equation, and you may think, well, hey, I would love to divide both sides by sine of x. But that's dangerous, because remember, sine of x could be 0 in value, and it is illegal to divide by 0, right? So I would suggest against dividing both sides by sine of x, because then you would lose solutions, x, for which sine of x equals 0. In fact, we do get solutions, values for x, that make this true when sine of x equals 0. So it's really inappropriate to divide both sides by sine of x, unless you consider sine of x equals 0 as a special case. So if you solve sine of x equals 0 separately and accept those solutions, ACCEPT, accept or bring in those solutions, that's fine. And in fact, that's a technique in differential equations to consider this thing separately. But in any case, bear in mind that you are going to get solutions here where sine of x equals 0. So it's suggested that you not divide both sides by sine of x. You will get solutions when sine of x is 0. Anyway, I would suggest a factoring technique. And if you're going to use a factoring technique, we eventually want to isolate 0 on one side. Here, I guess the right-hand side would be easier. And before we even do that, you might want to do a substitution, either now or later. Let u equal sine of x. That substitution may be helpful. Let's do it now. So when we go to u, we get 2u cubed plus u equals 3u squared. And this may be more comforting to you. It looks more familiar. We have an algebraic equation in u. It's a polynomial equation in u. Again, we have a lot of powers of u here. It may be safest to isolate 0 on one side. Let's subtract 3u squared from both sides. And at the same time, let's write the left-hand side in descending powers. So we get 2u cubed, and then negative 3u squared over here, because we're subtracting 3u squared from both sides. We still have plus u, and then equals 0. Remember, when we're setting ourselves up for factoring, we want to isolate 0 on one side. And then, how would you factor the left-hand side? What would you first factor out? The GCF. And the GCF is just u. So we factor out the GCF, which is u. The exponents decrease by 1 because we're dividing. 2u squared minus 3u plus 1 is the other factor. And we have a product equaling 0. But we can factor this further. And I'll give you a few moments to think about how to factor that. You can factor this old school over z, the integers. All right. Now you could also use the quadratic formula and get to the point, because we want to find the zeros. But you can factor this old school. We get 2u minus 1 and u minus 1. Remember, we need the same signs here because the constant term here is positive. Notice the outer product, negative 2u, plus the inner product, negative 1u. They combine to the linear term here, negative 3u. And now we have a product of 3 linear factors equaling 0. It doesn't get any better than this. We can go ahead and apply the zero factor property. This product equals 0 if and only if at least one of these factors equals 0. Let's go through them one by one. All right, so we have 3 cases to consider where u equals 0, where 2u minus 1 equals 0, and where u minus 1 equals 0. First of all, let's consider what happens when u equals 0. All right. U was sine of x. We want to solve sine of x equals 0. Not so fast. Think about it. What are all real solutions for sine of x equals 0? Draw the unit circle. Remember that on the unit circle, sine of x corresponds to the vertical, or y-coordinate, on the unit circle. We want to know where the vertical coordinate is 0, like y. Well, at this point, the east point, and at this point, the west point. And what are all the representatives, all the angles that correspond to these 2 points? Well, we have 0, pi, 2 pi, and so forth. We also have -1 pi, -2 pi, and so forth. Basically, all integer multiples of pi. X equals pi n, where n is in the set of integers. And in fact, we may not even have to write this now. It might be a better idea to collect these points at the end, because we might be able to exploit symmetry. In this problem, it turns out that symmetry doesn't help us too much beyond this, the pi n symmetry. But later on, we'll see examples where we can get some nice symmetry, and we may not have to solve these things factor by factor, case by case. But we do get solutions that correspond to all the representatives for east point and west point. Know that. Now for case 2. When does 2u minus 1 equal 0? Well, u was sine of x. Well, first, you could solve this for u. Let's do the algebra first. Add 1 to both sides and divide by 2. U equals 1/2. And then u was sine of x. Sine of x equals 1/2. Again, not so fast. Think about it. What are all the real solutions for sine of x equals 1/2? This will have solutions, real solutions, because 1/2 is in the range. In fact, it's a famous special sign value. You should get these solutions exactly. Go. All right. Well, first off, in what 2 quadrants will sine, S-I-N-E, be positive? In quadrants 1 and, think y or vertical coordinate, 2. So we're going to want solutions in quadrants 1 and 2. What's the arcsine of 1/2? What's the key reference angle in quadrant 1? Sine of what is 1/2? We're talking this kind of low point over here. Pi over 6. That's the flatter angle, pi over 6. So we want pi over 6 and its coterminal twins. So we want pi over 6 plus 2 pi n, where n is integer. That picks up all of our solutions in quadrant 1 from this case. But we also want all the brothers in quadrant 2. The most famous brother is 5 pi over 6, and we also want its coterminal twins. So put plus 2 pi n, again, where n is integer. And then we'll get all of the solutions for this equation for case 2, sine of x equals 1/2. All the representatives for this point in quadrant 1 and for this point in quadrant 2. Now, it looks like there's symmetry about this vertical axis, but unfortunately, we tend not to exploit symmetry about the vertical axis unless you have pi n, these guys over here. There's not a good way of exploiting symmetry here with the pi over 6 point and the 5 pi over 6 point. All right, what about case 3? U minus 1 equals 0. Solve for u first. Well, u equals 1. Oh, by the way, if you try to use symmetry on here, you get this ugly form. Ugh. Pi over 2 plus or minus pi over 3, and then coterminal. Anyway, going to the next part here. U minus 1 equals 0. Okay, u equals 1. Solve sine of x equals 1. Well, we want all the representatives for the north pole over here. The most famous rep is pi over 2, and we want all coterminal twins. Almost every student would write this down as a solution, as the solutions for sine of x equals 1. All right, so the final step is to bring everything together. The solution set is the set of all x in the reals, such that x equals pi n. Those were the solutions from case 1 over here. Or x equals pi over 6 plus pi n, or 5 pi over 6 plus pi n. So these all came from case 2. Or the North Pole situation, pi over 2 plus 2 pi n. That was our third case over here, where n is integer. And unfortunately, it doesn't really get much better than that. If you were to gather all of these points of interest on the unit circle, well, yes, we can use symmetry for the pi n case, case 1, x equals pi n, for east point and west point, but we're not able to exploit symmetry for the pi over 6 point and the 5 pi over 6 point. As for pi over 2, we're just picking up him and his coterminal twins. So unfortunately, it doesn't get much better than this. Now, if you were to try to check your solutions on Desmos, all right, now remember the original equation went this left-hand side equal this right-hand side. Now, if you try to graph y equals the left-hand side and y equals the right-hand side, that's y equals left-hand side. That's y equals right-hand side. Ooh, it's kind of hard to see the intersection points, but Desmos tries to figure them out. Pi over 6, 0 also. Pi over 2, 5 pi over 6, pi. You might have to zoom in to kind of see the intersection points better. Actually, it might be easier to subtract this from both sides, okay, and set this big ugly guy here equal to 0. Find the zeros of this guy. All right, and that may be easier to see. So we have solutions at x equals 0, x equals pi over 6, pi over 2, 5 pi over 6, pi, and so forth. And, and also if you go on, well, pi is the last one before we hit 2 pi. I want to mention also that if we were just asked to find the solutions between 0 and 2 pi, so what if we only wanted the solutions in this interval from 0 to 2 pi? Remember that 2 pi is coterminal with 0. So even though 0 is a solution, we're going to count it, but we're not going to count 2 pi. If we go around the world, we only have to go around half the world, really. There are no solutions in quadrants 3 or 4. But when we pick up all the solutions between 0 and 2 pi, what do we get? We get I'll put this in blue. We get 0. We get pi over 6, pi over 2, 5 pi over 6, and pi. We want to explicitly mention pi here. So your solution set would be 0, comma, pi over 6, comma, pi over 2, comma, 5 pi over 6, comma, pi. In fact, you don't even have to list these in order. You could go by cases. Case 1 gave us 0 and pi. Case 2 gave us these two guys. Case 3 gave us pi over 2. You don't even have to write this in order. Sets are unordered. Here, I did list the solutions in increasing order. And these correspond to the x-coordinates of these intersection points for the black and red graph, when I reframed it as a zeros problem. So 0, pi over 6, pi over 2, 5 power 6, and pi. Because it was harder to look at the left-hand and right-hand graphs. All right. Next, we're going to start using some identities.